Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College in Silicon Valley, and it's a great pleasure for me to welcome everyone in the auditorium and everyone listening or viewing on the web to this special lecture in the 13th annual Silicon Valley Astronomy Lecture Series. These lectures are co-sponsored by 4 excellent organizations: NASA's Ames Research Center, the Foothill College Astronomy Program, the Astronomical Society of the Pacific, and the SETI, or the Search for Extraterrestrial Intelligence Institute. And we appreciate their help in bringing speakers and doing publicity for this lecture program. I'm delighted to say that tonight our speaker is one of the most distinguished astronomers in the United States, Dr. Roger Blandford. Dr. Blandford, a native of England, took his degrees at Cambridge University, where he was supervised by the Astronomer Royal, Martin Rees. He joined the faculty at Caltech in 1976 and was appointed the Richard Chase Tolman Professor of Theoretical Astrophysics, distinguished named chair in 1989. In 2003, Dr. Blandford moved to Stanford University to become the first director of the Kavli Institute for Particle Astrophysics and Cosmology. At Stanford, he is also the Luke Blossom Chair in the School of Humanities and Science. He divides his time between the physics department and the Stanford Linear Accelerator Center, which is a national particle accelerator laboratory. His research interests include some of the strangest things going on in the universe: black holes, the origin of the universe, gravitational lenses, cosmic ray physics, and compact collapsed stars. Among the many international recognitions that he has received for his work, he has won the Eddington Medal of the Royal Astronomical Society and the Humboldt Prize. It's for me both a personal pleasure and a professional privilege to introduce to you, talking about black holes, the end of time or a new beginning, Dr. Roger Blandford.
Black holes have a very bad popular image. They are seen as agents of death and destruction, as torturers and annihilators. There have been several movies made about black holes. Here are 2 where the black hole casually ended the careers of several promising movie stars. There have been countless novels. Here the casualty was the English language. Black holes have inspired some of the most confusing scientific illustrations I have encountered, and some of the lamest cartoons. I'm entering the black hole now. Good grief, it's full of unmatched socks. There's a career here for all of you young people. You can't do worse. Here is a better book written by the late Carl Sagan, which was made into a famous movie. As is common in this genre, the plot became so tortuous that the only way the scriptwriter could escape was to invoke a variant on a black hole called a wormhole. This would allow you to pass from one place and time to something quite different. Sounds like a good idea, but the reality of wormholes is quite contentious. If you ever come across a black hole, as a physicist, I would not recommend the experiment. Here's an even better book from Dante Alighieri, Abandon Hope, all ye who enter here. It looks like a black hole to me. Black holes have been feared as threats to public safety. It was claimed that the large particle accelerators like this one in Switzerland would create black holes and swallow the Earth. Of course, this has not happened. And we knew that it would not happen because nature performs far more dangerous experiments all the time using cosmic rays. This is not the European debt crisis. See, people worry a lot about black holes. In short, they are thought to be bad. Now, I'm delighted to be here at Foothill College as part of the Silicon Valley Astronomy Lectures to try to redeem black holes, to persuade you that they are good and that they play an important part, an essential role in the life of the universe. I would also like to try and explain to you why physicists and astronomers like myself find them fascinating. It's time for me to start telling you a little bit about black holes. And for that I must begin with gravity. This here is Woolsthorpe Manor in Lincolnshire, in England. It's where Isaac Newton was born and where he formulated his law of gravity. Those of you who know about mathematics may notice the integral signs he carved in the wall. That's actually a cruel joke because Newton's great rival Leibniz introduced the integral sign. That's Isaac Newton. This is a house very close to Woolsthorpe. It is where I was born. I boast about this to my students. They are quite unimpressed. What's that got to do with anything? A common rural myth is that Newton watched an apple fall from a tree and realized that the fall of the apple would be described by the same agency as the orbit of the moon, and he invoked an invisible gravitational force to do the job. So here in the language of mathematics is the force, which you give the symbol F, and it relates it to the acceleration and the famous inverse square law of gravity. These equations are the foundation of most of the physics that we know about until quantum theory came along. Now jump forward 250 years to 1915. Albert Einstein formulates his general theory of relativity. He combines three-dimensional space and time into a single entity which he calls space-time. He discovers that space-time is curved when there is matter around. In addition, he does away with Newton's invisible force and describes the motion of the apple and the moon as a straight line in a curved space-time. Here is Einstein's equation. It looks very different from Newton's law, but the outcome is actually very similar. And the small differences from Newton's description are today measured accurately. Einstein's theory appears to be correct to about 10 parts per million. We have no grounds for doubting it as far as it can be used. Within a year of Einstein's formulation of his version of gravity, a German soldier, Karl Schwarzschild, who also happened to be professor of astronomy, discovered a strange solution to the equation that I just showed you. Today we know that it describes a black hole. There was a special spherical surface that surrounded this black hole, which we now call the event horizon, and from which nothing, neither you nor I nor even light, can escape. This is the point of no return. As I say, the event horizon. So there's a black hole, and surrounding it, shown graphically here, is this surface, this event horizon that the light cannot escape from.